In Chapter 5, Part 3, Calorimetry, we're going to start to look at the first way that we can calculate delta H of reaction. So calorimetry is a way that we can calculate the enthalpy of a reaction, or delta H. But we want to think about the amount of heat it takes to increase the temperature by 1 Kelvin of a substance. And we're going to measure that using calorimetry. Turns out there's two different classes of that, coffee cup and bomb calorimetry. We will talk about both of those in a little while. So the measure of heat flow, we all tend to these days, there are multiple different types of cups. In this case, I'm going to draw one that has a straw in it. So I use one every class period. It's maroon. It says howdy on it. It's kind of my favorite, but it's a corksicle. And so one thing we know is that if we put ice cubes in here, it's going to stay cold most of the day. And this is true if I leave my cup in my car in Florida in July. So the water in here is going to, at some slow rate, melt. It will stay much colder than it would have if I'd put it in a cup or if I just use a plain plastic water bottle. And so we can start to think about that. And so we want to think about how we're going to increase the temperature of our solution or our substance by 1 Kelvin. So as a reminder, Kelvin is a measure of temperature. And as we think about it in relationship to degrees Celsius, Kelvin is equal to Celsius plus 273.15. And so Kelvin is just a different system, and so we're going to use that. And one of the things we're going to think about in order to calculate that is determined by the heat capacity. And so we have both the specific heat capacity and the molar heat capacity. So heat capacity is just a general term for C, the heat required to raise the temperature 1 Kelvin. So that's heat capacity. Now we're going to think about specific heat capacity, which is C subscript S. And this is the heat required to raise 1 gram by 1 Kelvin. And so the heat capacity C is related to the specific heat capacity and the molar heat capacity, which is C sub M. And this is the heat required to raise 1 mole by 1 Kelvin. So the specific heat capacity and the molar heat capacity are going to be related to one another. So in general, specific heat, or C, is calculated by the heat transferred divided by the grams of a substance, or moles, and it will be also multiplied by the temperature change. And so if you may have also seen equations that look like Q equals C sub S delta T. And so that is also true. It is just a rearrangement of this equation. And so a couple of things about this. The mass needs to be in grams. C sub S, the units are typically joules per gram Kelvin. And delta T doesn't really have units. It can be in Kelvin. It is important to note. So we're going to call this our delta T note. Delta T needs to be calculated in Kelvin, but it turns out that delta T in Kelvin is equal to delta T determined in Celsius. And so the reason for that is the fact that 1 degree Kelvin equals 1 degree Celsius, although there are no degrees in Kelvin, so we'll erase that. What this is saying is that the difference between temperatures in Celsius and Kelvin is the same. And so you can calculate it in either one, provided you have converted between Celsius and Kelvin correctly. So as we think about these things, how do we want to start to think about this? And so we're going to work some examples. So how much heat is needed to warm 250 grams of water from 22 degrees to 98 degrees Celsius? And what is the molar heat capacity of water? We will come back to the second part. But specific heats are often calculated or solved for. So the equation we're going to use is Q equals m C sub s delta T. So if there are 4 components, provided you have 3 of them, you can solve for anything else. So in this case, I like to think about what do we know and what do we not know. So Q is our question mark, so we're going to solve for that. Our M in this case is 250.0 grams. C sub s is provided in this equation, so it's 4.184 joules per gram Kelvin. And delta T is going to be T final minus T initial, which is our 98 minus 22. Which is 76 Kelvin. Right, because degrees in Celsius and Kelvin is the same. So now we're just going to plug this into our calculation. So Q equals the mass, which is 250 grams, times C sub s, which is 4.184 joules per gram Kelvin. You know what? We'll just rewrite this. Since I ran out of space, Q equals 250.0 grams multiplied by 4.184 joules per gram Kelvin. Yikes, still so small. 76 Kelvin. Now, it's important to kind of think about this, and we can cancel out our units. Kelvin cancels, grams cancels, so joules is the only thing left. And so when we plug this into our calculator, we got 7.9 times 10 to the 4th joules equals Q. So we used our equation Q equals m C sub s delta T and just plugged in the values that we had. So the second part of this question here, so we'll just call that number 2, is what is the molar heat capacity of water? So the molar heat capacity is the amount of heat it takes to move 1 mole of a substance. So we have C sub s, which is equal to 4.184 joules per gram Kelvin. And so we want to convert from C sub s to C sub m. So we're going to actually use the molar heat or the molecular weight for water. And so what we're going to do is we're going to convert our 4.184 joules per gram Kelvin. We're going to multiply that by the fact that there are 18.02 grams in 1 mole. And when we do this, it would help if you could see what we had done, you'll get 75.3 joules per mole Kelvin. And so we can convert from C sub s to C sub m using the molecular weight. So let's look at another example. In this case, we are going to have the specific heat of octane, which is provided. So Q equals C sub s delta T. And so that's our equation. And so C sub s in this case is 2.22 joules per gram Kelvin. And so the mass in this case is 80.0 grams. And delta T is going to be 25 degrees Celsius minus 10 degrees Celsius, which is going to give us 15 degrees Celsius, also equal to 15 Kelvin. So from here, we can plug this into our calculation where Q equals m C sub s delta T. So we have a mass of 80.0 grams. Our C sub s is 2.22 0.22 joules per gram Kelvin, and our temperature difference is 15 Kelvin. And so in this case, when you plug it into your calculator, you'll get 2.66 times 10 to the third joules. So as we think about these, it's always really important to make sure what the units is asked for. A lot of times we'll see it switch to kilojoules because you'll notice most of these have relatively high heat values. So to calculate the specific heat, it's usually provided. And so as we start to think about this, this has been for pure substances. So what about if we want to calculate the heat of a reaction? So we can use something called coffee cup calorimetry. And so if the reaction occurs in water, and we assume that there is no change in the amount of heat to the system, we can start to calculate this. So in lab, you will do an experiment or watch an experiment that looks like this. So it is called coffee cup calorimetry because we use coffee cups. So in this case, we have a couple of things here. So we have a lid. It turns out we have 2 cups. And so the reason we have 2 cups is because you will have touched the outside one, and when you touch it, it's going to transfer some level of heat, and we want to be able to measure just the heat on the inside. So then we are going to use a stir bar. And so a stir bar is basically going to allow the solution to mix. The picture in the textbook uses a stirring rod, which basically is a stir bar connected to a valve that you will stir. And then we're going to have a thermometer. And so the thermometer is going to be under the water, and so it's going to measure the temperature of the water. And so it's important to note that this is a constant pressure. So we talked about how previously when we thought about that equation where delta H equals delta E plus P delta V or delta P V. In this case, we're at constant pressure, so this would be at P delta V. So constant pressure. And so the one thing that we kind of want to start to think about is, what does this measurement mean? And so we're going to measure Q equals C sub S M delta T or M C sub S delta T. Either of those is fine. I tend to write it M C sub S delta T. So when we think about this calculation, there are a couple of things that we want to think about. So we are going to measure, delta T of the water. And so it's important to note that the solution, so the heat of the solution plus the heat of the reaction is equal to 0. So in this case, we have a water-soluble reaction. So the reaction is going to happen in here. We're going to put our blue dots, and that's our reaction occurring. So it is impossible for us to put a thermometer on a molecule, but we can measure the bulk water temperature. So if Q solution equals Q reaction, or Q solution plus Q reaction equals 0, Q of the solution is equal to negative Q reaction. And so if we really want to measure Q of the reaction, so Q reaction is what we care about, that's going to equal negative Q of the solution, which is also going to be equal to negative M C sub S delta T, provided that is of water. So previously, we did not use this calculation. This is only true when we are measuring the temperature of the water. So if C sub S is equal to 4.184 joules per gram Kelvin, you can use this equation. If it equals anything else, you can't. So I use this equation because it makes more sense to me. If you don't, you'll need to know whether the heat is coming out of the reaction or going into the reaction. In this case, by just knowing that we're measuring the temperature of the water, which is going to be the surroundings, not the system, we can just invert the sign in this case. So in this example, a student mixes 50 mils of 1.0 molar HCl and 50 mils of 1.0 molar NaOH in a coffee cup calorimeter. The temperature increases from 21 to 27.5 degrees Celsius. Calculate the enthalpy change for the reaction in kilojoules per mole HCl. And then, based on this, our total volume is 100 mils. The density is 1 gram per mil, and the specific heat is 4.184 joules per gram Kelvin. So we know that we're going to use Q equals M C sub S delta T in this case. We also know that our balanced equation is HCl plus NaOH is going to give us NaCl plus H2O. So we're looking at an acid-base neutralization. So let's write down what we do know, because that's the easiest way to start. So we know that C sub S is going to give us 4.18 joules per gram Kelvin. Okay, that was kind of easy. Delta T in this case is going to be 27.5 minus 21.0. So in this case, our delta T is going to be 6.5 Kelvin. So now we've got two of the three values. So we also need to determine the mass. And in this case, the mass is going to be the total mass. And this is going to become important when we think about other questions. So in this case, our total volume is 100 mils. Then we're going to use the density of 1.0 gram in 1 milliliter to determine that our total mass is 100.0 grams. So now we can start to plug this into our calculator. So Q equals negative 100.0 grams times 4.18 joules per gram Kelvin times a delta T of 6.5 Kelvin. And so when we plug this into our calculator, we will get negative 2,700 joules. But the question asks for it in kilojoules, so now we're going to take our negative 2,700 joules, and there are 1,000 joules in 1 kilojoule, and so we're going to get negative 2.7 kilojoules. Now, the most common thing is to just slap a per mole underneath and call it good. Except if we remember back to chapter 5, part 2, what we need to do is make sure we divide by the quantity of moles that we have. So this is in fact wrong, and so we were not going to do that. What we are going to do is figure out how many moles we have in this component. So instead of calculating the number of moles from grams, we have 50 mils of 1.0 molar HCl. So we have 0.05 liters of 1.0 moles per liter. So this is just the molarity units being split out. And so at the end of the day, we're going to end up with 0.5. Nope. We're going to have 0.050 moles of HCl. And so in this case, we're going to now take our negative 2.7 kilojoules and divide that by 0.050 moles of HCl. And so from here, once we plug this into our calculator, we're going to get negative 54 kilojoules per mole HCl. So the reason we want to be able to think about this is now that we have this value, this is delta H reaction. So Q is per mass. Delta H reaction is often per mole. And so we can start to think about what that actually looks like in this case. But let's look at another example. So in this case, we have a 6.5 gram sample of solid sodium hydroxide dissolved in 100 grams of water in a coffee cup calorimeter. The temperature rises from 21.6 to 37.8 degrees Celsius. We'd like to calculate delta H in kilojoules per mole of the solution process. So it's important to note that we want to calculate delta H reaction for the dissolution of sodium hydroxide. So typically, we've not really thought about reactions as something dissolving or something else. We tend to think like A plus B goes to C plus D. So in this case, this is a reaction. And so what we're going to start to think about is that there are different types of reactions. So we want to assume, in this case, that the specific heat of the solution is the same of that of pure water. So we're going to, again, use our equation Q equals negative M C sub S delta T. So we can use this one, don't forget, because this is going to be the change in temperature of the water. And so let's start with the mass. So the mass on the previous question was 100. And so we have 100 grams of water. So is it just 100? But it's only 100 grams of water plus 6 grams of sodium hydroxide. So the mass is going to, again, be the total mass, which is going to equal 100 plus 6.50 grams, which gives us 106.50 grams. So our C sub S is provided, and it's 4.184 joules. It's only 4.18 in this instance. So we're going to take our 4.8 joules per gram Kelvin. And so the last thing we need to think about is our delta T, which is 37.8 minus 21.6, which is going to give us 16.2 Kelvin. So we can again plug this into our calculation. Negative 106.50 grams times 4.18 joules per gram Kelvin, and multiply that by the temperature of 16.2 Kelvin. So once we do this, we're going to get negative 7,211.7 joules. So the answer is asked for in kilojoules per mole, so we can easily convert our negative 7,211.7 joules by dividing by 1,000 joules in 1 kilojoule. So that gives us negative 7.2117 kilojoules. But again, it asks for it per mole, so we're going to take our 6.50 grams of sodium hydroxide. We're going to use the molecular weight of sodium hydroxide, which is 40.00 grams in 1 mole. We're going to get 0.1625 moles. When we divide by that, we'll be able to calculate the delta H reaction, and it's going to be negative 44.4 kilojoules per mole. And so in calorimetry, we can really calculate delta H reaction, but we're going to have to convert the heat that we calculated into heat per mole. So delta H reaction is almost always in heat per mole, so kilojoules per mole or something like that. So it's worth discussing bomb calorimetry. So bomb calorimetry is a combustion reaction, and so it's going to be constant volume, and it's set up just a little bit differently. And so in this case, we're going to have something called a bomb calorimeter. And so we're going to have 2 electrodes. So in here, we're going to draw our little blue sample. And then we're going to have a positive and a negative electrode. We're going to have a thermometer. And we're also going to have some version of a stirring rod. And all of this is going to be underwater. So in this container, so this is fully closed, we are going to light a spark between this positive and negative electrode and basically combust whatever is in there. We're going to then watch the heat transfer out and measure that in the water. And once we do that, we can calculate the heat of the reaction because there's no pressure change or there's no volume change, just a pressure change. So bomb calorimetry is used when we calculate the calories for any snacks. So if this blue dot here was in fact a goldfish cracker or a blue Skittle, they would explode that piece and measure the heat change, and that will tell you how many calories it's worth. So we are not going to do any calculations with bomb calorimetry. If this intrigues you, we talk about it a lot in some of our upper level chemistry courses.